The following limit I'm going to write down and state, I'm not going to prove it, though I'm going to give you the idea of the proof without actually writing it out. Is just something to realize, and something that could show up on homework, is to realize that you can cross horizontal asymptotes. I've mentioned that before. And in fact, I've written down this example before. The limit as x goes to infinity of sine of x over x. Note that this is not the same as sine of 1 over x. Is a function whose graph does cross its horizontal asymptote. This limit, in fact, is 0. Let's see it with technology here. Oops. Let's make that as well. Okay, we won't even see a graph at 0 because it'll be the x-axis. Sine of x divided by x. Let's not go out that far. How about just to say, just a 10 might be good enough here. I think I'll do this with y. -2 to 2 and make the y scale 0.1 unit apart. Oh no, let's go negative 1.1 to positive 1.1. A little closer. Here's the graph of sine of x divided by x. As x goes from 0 to 10, let's go out a little bit further. Let's go 0 to 50. You can see it's oscillating like the sine function oscillates, but the amplitude gets smaller and smaller. The x-axis, which is y equals 0, is a horizontal asymptote here. But it does touch the horizontal asymptote. That is okay. Doesn't happen with rational functions when you go out far enough, but it does happen with this function. In fact, it touches it infinitely often. I'm not going to prove that it's 0, but if you had to prove it's 0, what would you do? Well, essentially, because the sine function is always between -1 and +1, this graph is between the graph of y equals 1 over x and y equals -1 over x, no matter what x is. Both of those graphs, 1 over x and -1 over x, definitely go to 0 as x goes to infinity. We proved that that one did. This blue graph of this function is stuck between them. It's got to go to 0 as well. You're dividing by something that gets large, and in the numerator, you've got something that's not constant. It's oscillating, but it never gets above 1 or below -1. And that intuitively is why the blue graph is stuck between these two. It's squeezed toward the x-axis. And in fact, there's a theorem called the squeeze theorem that you can use to prove this as well, based on knowing that these functions go to 0 as x goes to infinity. But I do want you to know that this limit is 0, and that you can cross horizontal asymptotes like this. Same function, let's let x go to 0. Without looking at that picture, is this a rational function? Well, it is a ratio, but it's not a rational function because the numerator is not a polynomial. It's sine of x. So if you didn't know, if you had to guess, you might think, oh, I'm dividing by 0 when x is 0, so I guess I've got a vertical asymptote there. But no, it doesn't have a vertical asymptote. It's got a removable discontinuity. Sine of 0 is 0. The top is 0 when x is 0 as well. Because of that, it's conceivable that this limit is something non-zero. And in fact, it does exist, even though the graph has a hole in it, and it equals 1. If we zoom in near x equals 0 here, like this, and zoom in the y direction near 1, we see the graph is approaching 1. The calculator doesn't know there's a hole in the graph, but you do. But we can trace and we can see that as x goes to 0, y gets closer and closer to 1. Technically undefined when x is 0. But the limit exists n equals 1. It is a removable discontinuity there. And this is in fact a two-sided limit. You can also let x approach 0 from the left. In fact, this is an even function. And the limit as you approach 0 from the left will equal 1 as well. This is a limit fact that you should know as well. I'm saying it seems to be true based on numerical evidence. Later on in the course, when we talk about L'Hopital's rule, we will prove it's true. There are geometric arguments you can give for it as well, but we're not going to do that based on the unit circle definition of the sine function and thinking about right triangles and that kind of thing.